Yeah, no worries. Like I said, my name is Tyler. I'm a fifth-year grad student at Georgia Tech. On behalf of my colleagues at Georgia Tech and the Clever Project, I'll be presenting our work, which is an experimental investigation on the thermal extraction of lunar ice in permanently shattered regions. So the main focus of this work is we're trying to develop technology for in-situ resource utilization on the moon, specifically aiming at extraction of water ice from the permanently shattered regions where these ice deposits are located. One method that we can use is to implement concentrated solar thermal technology, which would be to set up an array of mirrors on the often permanently illuminated rims and refocus that sunlight down into these ice deposits for sublimation. And in this study, we have an experimental setup where we can simulate lunar conditions with an array of instruments to test out this hypothesis. And since NASA doesn't have the budget to send me to the moon, we have to do all the simulation in our lab. So to simulate the solar conditions, we have our high flux solar simulator. This allows us to emulate up to 5,000 suns worth of energy down to the size of a poker chip. That energy is then redirected into our concentrated lunar and rapid kinetics reactor, or CLARK, named after another solar-powered extraterrestrial. This includes molecular ion pumps for ultra-high vacuum conditions, pulse tube cryo cooler for those cryogenic cooling, as well as mass spectrometer to measure the partial pressures in the chambers. Inside CLARK, we have a packed bed inside a copper crucible. The packed bed is then embedded with an indirect solar receiver, which I'll get to in a second, as well as an array of T-type thermocouples. So there are some challenges that we have to overcome when it comes to concentrated solar thermal technology with lunar soil. The first being that it is highly reflective soil relative to what we're looking for, and due to the porosity in a vacuum, it is a very low thermal conduction. The solution that we've proposed is an indirect solar receiver. This would be a system that is embedded into the packed bed and would have selective coatings on the top, which are optimized for absorption and re-emission of the solar energy down into the packed bed, as well as walls that go down deeper into the packed bed, the regolith, so we can enhance the heat transfer and improve the sublimation that we can expect from these systems. So as I said, this is an experimental study, so we are testing various factors at different levels to see what has the biggest impact on the sublimations. The first is the inclusion or not of the indirect solar receiver. So either we just have the packed bed as is, or we embed a copper tube that is painted black into the packed bed. The next is we vary the porosity, since, as we've seen before, we don't know exactly what the porosity is of these systems. So we have two different levels. The limits of which we could do in this experiment. The lower limits, where if you're going to lower the indirect solar receiver, it doesn't stay in place any higher and I can't press it in. And the final factor we've done is the irradiation levels at two different values, 35 suns and 85 suns on average, to see how much of an impact that has on the sublimation rates. So as I mentioned, we have an array of thermocouples that are inside our packed bed at the top, middle, and bottom, as well as a fourth at the very bottom of the crucible connected to the cold head, so we can monitor the temperature gradient through the packed bed as the experiments run. The packed bed is allowed to cool down to a set point temperature and pressure before the experiment begins, which is at 0 minutes, where we start the solar simulator and allow the experiment to run for 30 minutes. And here we can see the low sun experiments, which show a steady and gradual temperature increase over that 30-minute time period. And then moving on to the high sun experiments, we can see the much higher heating rates, as well as higher final temperatures. A caveat is that I'm still in the middle of running these experiments. A lesson I learned when I was in engineering school is that all experiments take pi times longer than you expect. So we're still in the middle of these. That's why there's much larger confidence intervals. But the general trends we could see are the higher heating rates and much higher temperatures over this 30-minute time period. And we set a 30-minute time period because our quartz viewport doesn't like to be at these high solar fluxes for too long, so we don't want to damage more of our equipment. For all these experiments, the main metric that we're looking at is the amount of ice sublimated out the exit of the vacuum system. So here you have some of the interaction plots for the different factors at the various levels that we've studied. So we have the indirect solar receiver, which has the copper or none. We have the porosity at the two different levels, as well as the solar flux of the system, as well as their associated p-values on their interactions for the sublimation. The main takeaways for this is that the indirect solar receiver does make statistically significant impact on the results. The porosity does show some significance, but we're still waiting on final results. And the same thing with the solar flux is we only have a few data points for the high solar flux, so I can't make any conclusions on the results for that. But what we can do is look at the heating rates of these experiments in conjunction with the sublimations. And we see the actual inverse trend. So when there's a higher heating rates, we actually have less sublimation during these experiments, which is quite interesting. And we can also see the sublimation or the heating rates are somewhat uniform across. So this trend of sublimation rates decreasing with an increase of heating rates is something that has been shown in prior analytical studies. And the reason we believe this is that when you have a rapid heating rate, you have quick sublimation around the heating element, which leaves this desiccated layer of dry regolith. And this dry regolith, which is porous, just leaves, especially in a vacuum, is an excellent thermal insulator. So it prevents the heat from transferring to the rest of the packed bed, leaving the rest of it icy. We've actually shown this in some of our experiments, where you can see the walls in the center of the packed bed are still frozen, while the regolith that was around, the regolith simulant that was around the heating element has been desiccated and removed. So we're still testing the hypothesis that if we have a more gradual heating rate, we can allow a more even distribution of that heat throughout the system and have an increase in the total sublimation throughout these experiments. So in summary, we have demonstrated that concentrated solar thermal technology with the use of an indirect solar receiver application is viable for water extraction from these permanently shattered regions. We have preliminary results that showcase the critical factors that have impacted the lunar ice sublimation, and hopefully have this work to advance the ISRU through the innovative experiments, which we hope to use as model validation for some of the other work going on with the Clever team. As I mentioned, we're integrating this work with some of the computational models to refine and optimize some of these experimental conditions, all this to establish the moon as a pivotal resource hub for future space operations. And we can see from my artistic rendition of a lunar spaceport. This work was again part of the Clever team, which started with the reveals, and I'd just like to thank them and everyone involved and say thank you.